In the previous video you saw some information about Cook's distance, but there are other ways to think about the influence of cases on our model and on our conclusion. One way is to look at an added variable plot and look at cases that seem to be driving the direction and tilt of our trend lines in an added variable plot. Those are naturally going to be ones that are going to influence that particular parameter estimate. Another way is to measure influence through the concept of a DF beta or a DF betas, and we'll talk about those in a moment. First of all, the idea of a DF beta. The statistic DF beta has a subscript ij, and what it signifies is the difference between the estimated beta vector for the jth predictor when case I has been removed minus the estimated beta vector for predictor j from the full data. And so what it's going to measure is how much does case I change this particular beta hat vector, beta hat estimate, depending on whether the case is or is not in the model. So the thing you need to understand about DF betas is there is, it has a double subscript here. There's a DF beta for every predictor for every case in the data. So there's going to be n times p prime DF beta values. It is a very large amount of diagnostic information. And here in point 1, it just measures how much the predictor coefficient for predictor j is going to change when a case is removed. We're going to have every case measured impact on every predictor, and there's a lot of information to display, and we'll usually do it in some sort of a graphical display like a scatterplot matrix. And if you're going to use a DF beta, you'll probably need to understand that these are on the scale of measurement for the beta j scale, and so it's going to be essentially units of the response variable that these will be expressed in. What makes a big value of a DF beta? Well, certainly like a standard error, or big amounts of a standard error of the coefficient would be a big amount. So certainly relative to a standard error would constitute a big change. And that leads us to the next kind of statistic, a DF betas, S, because we are going to use the same kind of definition but standardized by the standard error of the coefficient. And so this would be a standardized measure. What would make a big amount of change? Well, something more than +1 or more than -1, or less than -1, I'm sorry, that would constitute a big change, a big amount in terms of standard errors. And so I like to use the DF betas version where I can understand the standardized scale. Here is a way to do this. I have estimated a model previously called modrat, and I extract the DF betas using the DF betas function on the model, and I'll save them in a big data frame called John, and then I'm going to display them for you in a scatterplot matrix function, the data frame John. The empty rows spot here means I'm going to use all of the cases. Remember, rows are cases, columns are variables, so I'm going to use all of the rows, all of the data observations, but I'm going to use columns 2, 3, and 4. That's what 2:4 means, is use the second, third, and fourth columns, which are going to correspond to the beta vectors for body weight, liver weight, and dose. I'm not going to display the DF beta for the intercept parameter just because it's not that interesting. In the scatterplot matrix, I'm going to have unusual cases identified with the ID.N option. And here is the display of DF betas. The way to read this would be to take a look at, say, body weight scatterplot with liver weight. Well, here are all the DF betas. Remember that DF betas that are like 0, 0, 0 would be right here, 0 would be right here. So here would be cases that, if they are removed, would not change the body weight coefficient and would not change the liver weight coefficient at all, because their DF betas values are about 0. However, if you look at rat or case number 3, you can see it's all off on its own here. It looks very unusual. And what it means is that the DF betas value for body weight is more than negative 1.5 standard deviations of a decrease if it's removed. So if this particular observation 3 is removed, the DF betas will be a negative 1.5 standard deviations. There's going to be a big drop in the body weight coefficient, more than a standard error drop. Not so much of a change in the liver weight coefficient, part of a standard error, about 0.4 or 0.3 increase in the coefficient for dropping case 3 from the data set. You can see case 3 happening again here. Very unusual impact on body weight, as we've discussed, but also a very big impact on the dosage effect. It would increase the dosage effect by more than 1.5 standard errors of the coefficient if it was to be removed. So case 3 is clearly a very big impact, but it's a big impact really only on the dose and the body weight estimates. Liver weight is not going to be, the beta hat for liver weight is not going to be affected very much. It's mostly body weight and the dosage coefficients that are going to be affected. As I mentioned, added variable plots can help see things, and here is the same liver weight, liver amount rat data, and you will see in the added variable plot for body weight that case 3 up here is going to have something very big to say about the negative trend in the beta hat for the body weight coefficient. You can see it's very important. We saw that through the DF beta. For liver weight, case 3 is not even one of the identified cases. It's one of the unmarked ones, and so there's really not going to be any impact on liver weight for case 3. And for the dosage, you'll see case 3 is a very important part of the dosage story. It had a very abnormally high dosage. It had a very abnormally high amount of the drug in the liver, and case 3 is very important to establish the dosage effect. That's how you would read added variable plots for influence. Another command that is helpful is the influence plot command. You supply a model and how many cases you'd like to be identified specially, and it spits back for you some printed output about studentized residuals, the leverage, the Cook's distance, so you can see unusual values. And you also get a plot, of course, that comes with it, like this. And we have studentized residuals on vertical axis. We have the leverage values on the horizontal axis. And remember, those are the two components to Cook's distance. And the size of the circle tells you the Cook's distance impact on the parameter vector. And again, because the size or the area of the circle is so big for case 3 in the rat data, it's not surprising it has the biggest Cook's distance. That will be the influence plot. We've talked about the influence index plot before, and here we are again for the rat data. We have Cook's distances, case 3 up here, studentized residual, nothing remarkable, no unusual Bonferroni p-value, and we have an unusual leverage for the rat data. Another aspect of residuals that we haven't talked about very much is the normality of residuals, and how it matters, what it does, how does it look. Well, what I'm showing you here mathematically in the top of overhead 28 is that the residual vector is found by taking one identity vector minus the identity matrix minus the hat matrix times the response values, and that just expresses the residuals as 1 minus the hat matrix, the projection matrix, times the random errors. Okay, so the residuals are a function of the random errors, and in particular, the ith residual is the ith error minus a weighted sum of the other errors in the data set. And the point of all this is that you're supposed to remember from an earlier class in statistics that summing random variables tends to produce normal bell-shaped behavior from the central limit theorem result. And so if we have any kind of moderate to large size data set, the second part of this summation will produce a normal variable, and so residuals will tend to have more normal behavior than you might otherwise suspect. And so therefore, on the third point, normality of errors is not quite as critical of an assumption for regression analysis. Regression analysis tends to work well even if the errors are not terribly normally distributed because of this nice feature of summation in an actual data set. If you do want to assess the normality of your errors, you would estimate a model like what I have done here for the mother and daughter's heights in M1, or a model based on the transaction bank data called transmod, and you use the QQ norm function on the residuals from each model, and you get plots that look like this. This first QQ plot is for the mothers and daughters data, and this second QQ plot is for the transactions data, and a set of residuals that is very normal would tend to be in a very straight line, more like this mothers and daughters. The more that the QQ plot is in a straight line, the more normal the observations are that you're plotting, and we're plotting the residuals here. You can see that the transaction data is not quite so linear, suggesting that the errors there are not really closely normal. Don't panic though, remember that regression analysis works really well even if the errors are not exactly normal. Here's another little example using some occupational prestige data in the Duncan data set from the car package. We made a model that would try to explain the prestige score of an occupation as a function of the income, the education level of the occupation. And for this data set, I've asked to make an influence plot to show unusual cases. We have a printout of some unusual cases: minister, reporter, conductor on a train, a contractor, a railroad engineer. I believe these are somewhat old data, historical. And here is what the influence plot looks like. You can see from the large circles that minister is a very influential big Cook's distance in this data set. Removing minister from this data set will cause the biggest change in the estimated parameter vector. And you can see the problem for minister is primarily being driven by the large positive studentized residual. Evidently, ministers have a much higher prestige for their job relative to what their education and their income is. They evidently have a substantially higher income than what prestige than what we would expect based off of their income and their education. Whereas a reporter has sort of an abnormally low prestige given the amount of pay and the amount of education that they would have. So remember that the large circles are influential cases. The vertical nature tells you how far the prestige is above or below what we would expect, and the hat values measure the strangeness of the income and education profile for these professions. As I suggested earlier with outliers, what you might want to do is just temporarily delete them and take a look at what happens to estimates for the new subset. And so what I've done here is made a new model called Model Duncan 2 that has taken out the minister. So I've made a subset of the Duncan data. Not equals, exclamation point equals means all of those but not minister. And we're going to compare the estimated beta coefficients for the original model to this reduced one without minister. And you'll be able to see the estimate vectors. Estimate 1 is the full model, and estimate 2 is from the reduced. And you'll see that the intercept and income and education coefficients are fairly similar. You can see, though, that if we delete minister from the data set, the impact of income on prestige goes up quite a lot. Part of a standard error, or basically one standard error goes up. You'll notice the standard error vectors are about the same. The variations are not changed much by getting rid of the case minister, but the education and the income effects are affected by the removal of minister, and you'd be able to see how it would work, and you'd be able to discuss that in your report. Hope this is helpful.